All right. So we're actually skipping chapter 12 for the moment because we need chapter 13 to do the lab. So on your average 328P chip, whether it be a DIP package or a TQFP package or QFN package, at some point you need to leave the digital realm. I know that's our comfort zone. We like ones and zeros. It's really easy to figure out because there's only two options. But most things in life are analog. So we have this thing called an ADC. This is not the right thing for me to be in. So this is what we're going to cover today. Why do we need an ADC? What the heck's going on? We've got our registers. And then sort of the thing that isn't going to be too much of a big deal today, but will be for the rest of time for you, is signal conditioning and how you have to condition an analog signal to make it fit into an ADC. So your average signal chain for any real-world signal is going to come from the real world, whether it's light or sound or vibration or heat. There's going to be some physical phenomena, and you're going to have a sensor or a transducer. Whatever that is doing, it's going to translate that physical phenomena into some kind of electrical phenomena, whether it's a current reading, so the current may increase, or a voltage reading, usually. It might be a resistance that changes, but something electrical that we can measure. And really, I've just covered Ohm's law, right? Resistance, voltage, or current. And I will be needing my my tablet today, so let's get that right now, get it ready. All right. So whatever that physical phenomena is, it's going to be turned into an electrical phenomena by the sensor. And then we're going to need to turn that still analog but electrical signal into something digital. Now, what's the problem with a digital signal versus an analog signal? Is one better than the other? It's made up of ones and zeros. If we combine multiple bits of ones and zeros, we can get discrete values up to any number. Why would it take an infinite amount of bits? Let's just say I have a 0 to 5 volt signal. Couldn't I just use 3 bits, right? 0, 1, 2, 3, 4, 5, 6, 7 will give me 3 bits.
I'm just thinking about the accuracy of that value.
It's a good thing to think about, the accuracy. If I only record a volt, right, 0, 1, 2, 3, 4, 5 volts, what happens if my analog signal is 1.5? Does that read as a 1 volt or as a 2 volt? Your tolerance fits into this, yeah. So the problem with a digital signal is it's discrete. There's only going to be so many different values that we can represent with a finite number of bits. Whereas an analog signal, you can always find a value in between two values. If I tell you to pick a number right in the middle of 0 to 10, 5. Now find me a number between 5 and 0. 2.5. And then between 2.5 and 0, 1.25. You take the 2, you divide it in half. You take the 0.5, divide it in half. Just do them together. And we could keep going. Half of 1.25 is 0.675. And from there, right? We could keep dividing by 2. There's always. What about between 0.001 and 0? Is there a number in between those? Of course there is. All right, we could go 0.0005. So that's the problem. That's the main problem with a digital system is it's finite, it's discrete. There's only so many ways, but we can make a good approximation. So an ADC has some analog input signal. On the bottom it's recorded as Vin. And usually there's some way to say, hey, start doing a conversion. Take whatever the analog signal is at that moment and convert it. So when you see a pulse on this, it says, hey, start the conversion. Then time will pass. That's my clock. Time will pass, and then we'll get a digital output, some number of bits. Now, in this case, this is an 8-bit ADC. That means it can represent 256 different voltage levels. And the way it determines what those are is there's some reference voltage. Actually, there's two. There's a high and a low reference voltage. So here, the low voltage reference is 0 volts, and here it's Vref. When you get a signal, a digital signal that is all ones, that is Vref. When you get 0, 0, 0, 0, 0, 0, that's your low signal. So this basic block diagram has all the pieces we need to talk about any ADC. Voltage reference, analog input, digital output. So when we're characterizing an ADC, not all ADCs were created to do the same thing. Some were created to do very slow measurements like temperature over time. Some were meant to do things very quickly, like, say, a sound converter. You're listening to a microphone. You've got to digitize that at a certain rate to be intelligible. Some were meant to go really fast, software-defined radios these days, which have bandwidths of 100 megahertz for the very nice ones that you can get in a research setting. You've got to be able to sample 100 million times per second. All of that feeds into conversion time. How long does it take for you to get a reading? From the time you say go, how long until it's got an accurate, and that's sort of the key here, an accurate representation? Because you could just read it as soon as you said go, but it wouldn't be accurate. You would lose what we call resolution. So resolution is the idea that we have between 0 and Vref. This is our continuous range here. Our resolution says, all right, let's suppose that we have only 1, 2, 3, 4, 5, 6, 7, 8 bins. That would be a total number of bits equal to 3, right? That would be from 0 to 7. So this is an output 0, 1, 2, 3, 4, 5, 6, and 7. Pretend that I'm a better artist than I am, and these are equally spaced. So our resolution is the size of this block. Now suppose that Vref was 8 volts. Just to make the math easy. How big is this block if there are 8 total blocks and we go from 0 to 8 volts? It's just a single volt. But what that means is that any analog voltage from 0 to just under, we should say less than 1 volt. Less than 1 volt. So if the input V is greater than or equal to 0 volts and less than 1 volt, that means it's going to give you a digital output of 0. Now that's not really handy, right? It means that anything between 1 volt and 0, 500 millivolts, 750 millivolts, 200 millivolts, 1 millivolt, all going to give you a 0. So the step size is this 1 volt here. Resolution is the number of bits. So this is number of bits. And the step size is usually measured in volts. But to calculate the step size based on the resolution, you also need the voltage reference. If I had made the voltage reference 5 volts, it would have been 5 divided by 8. Okay. My resolution is number of bits. So my resolution on this fake one would have been 3 bits of resolution, which means I have 8 bins. That's 2 to the 3 is 8 bins. And then Vref would have been 8, so 8 divided by 2 to the 3 is 1 volt. Okay, so that's conversion time, resolution, Vref. This next characteristic, parallel versus serial, says, how do we get the digital data out? Do we read it all at once? In the case of the previous example here, all 8 bits are there. So we can read them all at once. Serial is the idea that we're going to read one bit out at a time. So many external ADCs that you can purchase, they will actually have a serial protocol that you communicate over. One might think that that would be slower because you could only read one bit at a time, but that's not always the case. Because with parallel transmissions, it's possible to get a lot of crosstalk, so you might have to read slower for parallel. Whereas serial is only one line, you can do a lot of noise reduction, you put buffers in, it's nice and simple, and you can run it at a much higher baud rate than parallel. And finally, a major feature of many ADCs is they can read more than one analog signal. You can put 4 in and then choose which one you want to read. Or you put 8 in and choose which one you want to read. The version that we showed here just has one analog input. Okay. More complicated ones will have multiple inputs and you get to choose between them. So the characteristics of an ADC: conversion time, resolution, VREF, step size, the output type, and the number of input channels. So here is the ADC 0848. It's an analog devices chip, I believe. It's got 8 input channels. It looks like it has an 8-bit parallel out. 8-bit parallel out right here. Okay. And it's got a few control signals and its reference. Okay. Here it's got an analog reference, but it still requires a digital supply. So let's just, based on what we talked about with step size and resolution, because that's a big part of this chapter, we say that our resolution is 8-bit. Our VREF is 2.56 volts. What will the digital output be if we put in 20 millivolts? So how do we figure that out? First off, what is our step size? How do we figure out what our step size is? Not quite. Not quite. You said that our step size was equal to 2.56 volts divided by 8. And it's not 8, it's 2 to the 8. It's the number of bins. So if it says it's an 8-bit resolution, that means there are 256 bins. Now what is 2.56 divided by 256? A number. You want to break out a calculator for this one? 2.56 divided by 256. Really? Say it louder. 0.01. It's 256 divided by 256. It wasn't intentional, I promise. 0.01. I thought you were like messing with me. Like, oh yeah, all right. Okay, 0.01. So I wasn't. I was asking you a very simple question. Like, I didn't choose these numbers completely at random. They're designed to be done in your head. So, all right, our step size is 10 millivolts. So what does a 20 millivolt input reading come out as digitally? Take 20 millivolts, divide it by your step size. That units cancel. So what do we end up with? Do you want to pull out a calculator for this one too? It's 2. You sure?
Well, I can check.
You want to check? Now I am messing with you. All right, it's 2. So the digital output will be 2. All right. Now, some people may argue that actually the result would be a 1 because it's the less than or equal to, right? So technically that should be, right, anything between 0 volts and 9.99999 millivolts. Let's not quibble over a thousandth of a millivolt, all right? We'll call it just divide the input signal by the step size, and that's your reading. If it happens to come out exactly right, well, buffo for you. But chances are we're measuring a time-varying signal, so there'll be a little bit of noise one way or another, and we won't have to worry about us being off by one least significant digit. Okay, so there we go. calculating your digital out is V in, your input voltage, divided by the step size. Very often you won't be given the step size, you'll just be given the resolution, 8 bits, and the reference voltage, 2.56 volts. All right, so AVRs actually have an ADC built into them. On the 328P, it's actually hooked up to port C. All right, on the ATmega32, they have a lot more stuff going on. All right, but things to note, we have a 1.1 volt reference. So if you're doing calculations, internally we provide a 1.1 volt reference. That's not the only reference we can use. In fact, most of the time we don't use this one, but it is available to us. And we have 8 single-ended inputs. Single-ended, you've all seen the analog discovery, right? On the oscilloscopes there, every time you want to do a reading, you have like the orange striped wire and the orange wire. That is a differential probe. It will measure the difference between those two wires. Most of the time you take single-ended measurements by sticking the striped wire to ground, which means you're just taking an absolute reference to ground. But you could do it across some resistor and measure the voltage drop. So the 328P only has single-ended inputs. Other microcontrollers can have differential inputs, and we'll talk about that. Okay, one of the things, especially when we start dealing with analog circuitry, is we have to consider noise. Noise is unwanted electrical activity on your signal. Suppose you want to digitize this sine wave. Okay. Digitizing the sine wave is just a matter of taking samples, measuring their voltage with sufficient resolution, okay, so that we can get those samples out. Okay. Now imagine there was unwanted noise on this signal. Something like this. Some high frequency oscillation. All right. If I zoom in on that high frequency oscillation, backdraw in red. Let's just look right at the top there. So here it is starting to crest. I was originally sampling here and here. Those were my two samples. Now let's look at that high frequency noise. We've zoomed in, so it's going to be a little bit more visible. All right, so this is the actual signal. It's following along the path of the sine wave, but there's this low magnitude, high frequency noise. So now look at where those samples are actually taken. This sample is taken up here, and this sample is taken down here. So instead of reconstructing this nice arc here, we actually see, it looks like it's actually decreasing, which is bad. We definitely have a sine wave that's increasing at this point, but because of the high frequency noise, it looks like it's decreasing. So high frequency noise, bad. We'd like to get rid of it. So what that usually means, all right, if we have high frequency noise, it could be in one of two places. Go back to our first ADC here. Erase a link on slide. Our high frequency noise could be on the analog input itself. But that's not the only place that high frequency noise can appear. It can also appear on your voltage reference. The easiest way I found to explain the phenomena of noise being on your voltage reference is picture a slinky. Everybody knows what a slinky is? Okay. A slinky goes around and around in a helical fashion, right? So imagine you're looking at the right side. It's going to helix around every time. The distance between the coils, that's your step size, right? Okay, a bunch of equally spaced containers. Now, imagine I stretch the slinky a little bit more. What happens to the width between those bins? Gets bigger, not by much, right? If I move this an inch and say there's 100 coils, I'm not moving it by much. I'm moving it by 1/100th of an inch. That's barely perceptible to the human eye. Okay. Now suppose I go from a known position and I shrink it by an inch. What happens to these step sizes? They get smaller, again, by a very small amount. Now imagine that I take this slinky and I do this to it. What happens to the size? What? Yeah, it does this. It does this. It moves constantly. Now, not only is a single step size moving like this, but it's riding on other steps that are also changing. So you take, 100 of these steps and they shrink by just a little bit, and suddenly you can find that you're reading, even though you put in a constant voltage, the constant voltage is, say, here at my eye level, you increase it a lot, suddenly I've moved several bins away, and then I shrink, and I've moved several bins in the other direction. Try it with a slinky sometime when you don't want to study, all right? And think about it. Next time you see a slinky in a toy store, don't just think about how much fun it is to throw it down the stairs. It's an analog for a digital to analog, or an analog to digital converter. So here's what we do. We use some analog circuitry to block analog noise. I am not going to go into the time varying analysis of this. I'm just going to say that an inductor blocks high frequency AC and allows DC, direct voltage, direct current. So high frequency noise is going to be blocked. So if I've got a VCC that's noisy, on this side of the inductor, I will have a VCC that is clean. It does, so I might go from a 5-volt signal that looks like this, and what I will get out of that signal, because of the inductor, is I'll get a much cleaner signal. And that's what I send to my analog VCC. All right, I need to power the analog circuitry. Oop, go back for a second. Also, I will put inductors. I will put capacitors to ground to further smooth out the signal. Right? Capacitors are also smoothing circuits. This is not just a polite suggestion. Here I have a circuit from a research project we did where we were sensing temperatures underground. It is not just a polite suggestion. You really do need inductors, capacitors on your analog VCC and your analog reference line. Yes, this is a resistor schematic. It really is an inductor. That is a real schematic that did get published. It just so happened that the inductor we were using had the same footprint as the resistor, and so we got lazy and called it an inductor. But it looks, this is the symbol we were using for resistors, so it seemed okay to use the squiggly line. Inductors are hard to draw in a CAD program. There's arcs. Stop judging me. But it is a real thing, all right? It's not just a polite suggestion. So when you are evaluating hardware, look at its analog conditioning, all right? This is just to keep the reference stable. We said that it could also be here, and there are different ways of dealing with that. But just to keep the reference clean, we can throw in some inductors and capacitors. Now, how do you choose these inductors and capacitors? How do you choose between a 100 nanofarad capacitor and a 0.1 microfarad capacitor? I'll let you think on that for a moment. Why would I choose a 100 nanofarad capacitor over a 0.1 microfarad capacitor? Why are you laughing?
The same thing.
Yeah, they're the same thing. 0.1 microfarad capacitors are the same thing as 100 nanofarad capacitors. As a convention, however, people don't sell 100 nanofarad capacitors. They either sell something in the picofarad capacitor range or the microfarad capacitor range. Now, they will sell you a 10,000 picofarad capacitor, but they won't label it a 10 nanofarad capacitor. They don't, for whatever reason, they label them in puff or microfarads, but not nanofarads. Something to keep in mind if you're ever looking for a capacitor. Why won't they sell me a 100 nanofarad capacitor? Look for a 0.1 microfarad capacitor and you'll find it. But the question was, how do you know what values to use? Here I used a 10 microhenry inductor. The answer is in the data sheet. Okay? Somebody designed this processor, and they did a hell of a lot more testing on it than you are gonna. They know. And they will tell you. Why will they tell you? Because they want you to use their chip. So they want to make it as easy as possible for you to plunk this down into your product and make use of it. They don't want to make it difficult for you. They want to make it easy. So they'll tell you, use a 10 microhenry inductor. It's the recommended inductor. Use a 100 nanofarad capacitor between AV ref and ground and AVCC and ground. They just tell you. So just read the data sheet. The answer is always in the data sheet. When you ask me a question, chances are the answer is in the data sheet. Okay. Analog considerations. Okay. Now, let's get more into the AVR ADC. The AVR ADC is a 10-bit ADC. Means it has a 10-bit resolution, which means how many steps does it have? 2 to the 10, which is 512, 1024. Those first 10 powers of 2, you should really get tattooed on the inside of your eyeballs. The other thing to remember is 2 to the 10 is about 1,000. About 1,000. 2 to the 20 is about 1,000,000. All right. We call it 1K and 1 meg. Okay. But the first 10, 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, and 1024, you should just have that list. Okay. But it is 10 bits, and we have an 8-bit processor. So we have 2 options as how we look at it. We have 2 registers. One's called ADC-H and one's called ADC-L. This is where the digital result of a conversion gets stored. So we can look at it such that the upper bits are in the high and the lower 8 bits are in the low. Or if we don't need a full 10-bit resolution, if we only need an 8-bit resolution, how many bins are there in an 8-bit resolution? 256. So if we only need 256 bins, we can look at the entire result left adjusted. So here's bits 9 through 2. All right, and we can access it just as a byte. So we don't have to worry about any 16-bit problems. We can just look at it as 8 bits. So there is a bit in one of the control registers called the ADLAR, left adjust. Okay, do you want to left adjust the register? If you put a 1, it will left adjust, and you will get an 8-bit resolution. So this means 8-bit. If you don't want to left adjust, you get your full 10-bit resolution. So that's where the result gets stored. It's just a number. That's the easy one. These bits, these unused bits, are guaranteed to be 0. It's just how it works. Okay. The next thing I want you to know is how many input channels the 328P has. Okay. The 328P uses a multiplexer topology to choose between options. There are 4 bits in the mux field that tell you what input you want to read. Okay, depending on what you put in here, that'll tell you what you get. You can read any one of the 8 inputs. You can read the reference, so that's that 1.1 volt reference. You can actually try to convert ground. Why would you want to try to convert ground? Well, what happens if you convert ground and it doesn't give you a 0? It's not ground. So it's a check. You can check things. You can also get a temperature sensor. You get a temperature sensor for free on the 328P. But it's a really crappy temperature sensor. I think it's like plus or minus 10 degrees C. Okay? That's 20 degrees C. That's a difference between, let's say, 50 degrees C, which is too hot to touch-ish. So if your chip gets to 50 degrees C, it's going to burn you, down to 30 degrees C, which is just kind of nice weather. 20 degrees C is the difference between freezing and a slightly cold room temperature. All right. So it's enough to tell you if you're burning alive or in an icebox. But it is there. Okay, it can give you a hint at the temperature. Don't quote me on this number. If you really want to know what this number is exactly, do you know where you should go? To the data sheet. And if you look in the analog to digital converter section, it'll say, hey, there's a temperature sensor, and it'll give it to you. It might only be plus or minus 5, but it's certainly not accurate. The other field in the AD MUX register is REFS, which stands for reference selector. Reference selector. And we have a lot of options when it comes to the reference. I know I said we only have a 1.1 volt reference. That's the only provided reference. We have a lot of options as to what we can choose here. We can choose the internal reference. We can also pump in a very clean voltage, any voltage we want really, to the AREF pin and use that. Finally, we also have the option to use whatever the analog VCC voltage is. Now on the Atmel explained mini boards, this is tied to plus 5 volts. Probably most of the time we're going to use that reference. How do we choose that reference though? To choose that reference, well, here's the table. Okay. What we want to make sure we do is we want to make sure that the MUX has chosen that input to send forward, and we want to turn on this MOSFET so that data flows through it. So to use analog VCC, we want to set RefS1 to 0 because this is the 0 input, that's the 1 input, and we want to turn on the MOSFET. You can see actually how all of these work. If we turn off the MOSFET and we set this to 0, what does that mean? Well, AVCC is chosen, but it's not sent through the MOSFET. So the only path in here is through AREF. If we choose 1, 1, that's going to pass the internal reference through and turn on the MOSFET. And that's exactly what it says. The one thing it says is if you select 1 and 0, that would try to send the reference through, but wouldn't let it through. So it's just reserved. Don't do that one. Okay, because it doesn't make any sense to turn on the internal reference and not use it. So it just says it's reserved. So a lot's going on in this register. We've got a reference select field. We've got an input select field. and we have our left adjust register. This is for the 328P. It's the one we'll be using in lab, probably next week for most of you. I'm doing on time. There are more complicated topologies. This is for the AT Mega 32, and something very similar exists on the Mega 2560. Okay, you still have 8 analog inputs. The band gap reference is a little changed, but some of them have a multiple purpose. We can use these as part of a differential chain. So we can say, all right, I'm going to send, choose a different color here. I'm going to choose ADC7 and send it to the plus side of this gain. And then I'll choose maybe ADC0 to go through this mux. So what this value here will be, this will be ADC7 minus ADC0 multiplied by a gain. So let's say you're measuring some small resistor in a Wheatstone bridge. You only want to measure the voltage drop across that resistor in the Wheatstone bridge. Okay, it's going to be a small change. Maybe it's a load cell. Maybe it's just a Wheatstone bridge. It's a small voltage change that's going to occur. So you'll take that small voltage and you'll apply a large gain before, where's my pen? Apply a large gain before it goes into the ADC. So suppose you're only getting 0 to 0.1 volts drop. You could apply a gain of, well, what are our optional gains here? You could apply a 200 gain to that. So 0.1 volts times 200, that would give you what? 20 volts. That's a little too much. But if your change was very small, say 0.01 volts, then times that by 200, that's 2 volts. That would nicely fit in your 2.56 volt reference. So that would be pretty nice. But the idea is the analog to digital converter has fixed size bins. So if you can, in the analog domain, make your signals swing, max to min swing, larger, you'll get a better chance of using all of those bins. So there are many things that are just single-ended, no gain, but there's also the ability to do differential inputs with a mixed gain. We don't have that on the 328P, but you need to know that stuff like this exists, okay? Because if you get an external ADC, because the ADC on the 328P, it's not a one-size-fits-all. It can only go so fast. It's only got a 10-bit resolution. You might need a 12-bit or a 16-bit resolution. You might need to go faster. You might be able to get away with only an 8-bit resolution, but need to go much faster. So those are all things that you need to deal with. So be aware that you can get ADCs that do this. So there is a control register for the ADC. It's actually a control and a status register. So the ADCSRA is analog to digital control and status register. Things that we can control, we can turn it on, we can enable it. That just means it's going to be ready to work. We can start a conversion. We can enable interrupts because the ADC can trigger an interrupt. And we can choose a prescaler. So this is its own field. This prescales the time or the clock. Because, excuse me. The way the ADC actually does its job is it does what's called successively approximates. How many of you ever played a guess a number game and I say higher or lower? That's a successive approximation. If I tell you that I'm thinking of a number between 0 and 127, what would your first guess be if you wanted to do the minimum number of guesses? What? Half that. What's half of 127? Think about it like this, right? There's 0 to 127, so that's 128 values. What's half of 128? 64. So it's not 64. It's lower than 64. 32, that's halfway between 64 and 0. So 32 is too low. So now the way you figure it out is what's halfway between 32 and 0? 16. So add 16 to 32. 48. 48 is too high. So what we've been doing is we started by saying 64, then we were looking at 32, then we looked at 16. Now we're going to look at a difference of 8. So we know it's between 48 and 32. So what's 48 minus 8? Or what's 32 plus 8? 40. 40 is here. 40 is too high. So now we go 4 up from 32 or 4 down from 40. 36 is also too high. So now we go 2 up from 32 or 2 down from 36. 34 is too high. So you go 1 up from 32 or 1 down from 34. 33 was the number in question. So how many guesses did that take? 1, 2, 3, 4, 5, 6, 7. It just so happens that 2 to the 7 equals 128. That's the way the math works. Okay, you can always guess a number between 0 and 100 in 7 guesses or less because it's less than 128. Okay. But what does this have to do with the clock? Why do we need a clock? Well, it's going to guess on a metronome scale. It takes some time to do the math. It's got to go and it's got to keep track of what step is it on. It's got to add to this. If you go too fast, it doesn't have enough time to do the full math. So it will make a guess in the correct direction, but not as accurately as it should. So we have to make sure, and this is the one big thing, we have to make sure that the clock that goes into the ADC is not more than 200 kilohertz. Regardless of what our CPU frequency is, we are locked. We cannot go faster than 200 kilohertz on the clock, because that is the time it takes to go from one step of guessing or one step of approximation to the next. So, grab a calculator for this. If we have 16 megahertz as our clock frequency, how do we determine the minimum prescaler? Well, we know that we have a 16 megahertz clock. 16 megahertz divided by x has to be less than or equal to 200 kilohertz. How do I rearrange this algebraically to solve for x? Speak up. Yeah, switch x and 200 kilohertz. So what I end up with is 16 megahertz divided by 200 kilohertz must be less than or equal to x. Did I do that right? Yeah. So what happens when I take 16 million and divide it by 200,000? I get 80. So 80 must be, or rather my divider must be greater than 80. So what does that mean in terms of what can I choose here? Can I choose 64? No, because it's got to be at least 80. So my only option is divide by 128, which means my actual clock will be 16 million divided by 128 is 125 kilohertz. Now, this is exactly how we choose. We've got these prescalar bits in the prescalar field. This is 0, 1, 2, 3, 4, 5, 6, depending on what we choose. Okay. So how do you program this thing? It's really not that complicated. You want to make sure that whatever analog pin you're reading from, so they're all on port C. So on the Arduino, they're labeled A0 through A5. We've got them labeled as C0 through C5. That's okay, though. You want to make sure that whatever wire you hook up to the analog sensor, okay, whatever wire you hook up, you want to make sure that it's set as an input, not an output. You can't read in an analog value when it's set as an output. Because if it's an output, there's only going to be two voltages, 0 or 5 volts. You got to turn on the ADC, okay, because by default, it takes a lot of power to do analog conversion, so you don't want it on all the time. So you have to turn it on using the AD enable bit. You have to select the conversion speed. That's the AD prescalar field. Oh, it says it right there. You have to set the voltage reference. That's ref S, the ref S field. You have to select the input channel. That's the MUX field. C0 is input 0. C5 is input 5. So if you want to read in from input 5, you put 5 in the MUX register. The most important part here is then you must write a 1 to the start conversion bit. You set it up, but then it will just sit there. It won't actually do any conversions until you say, go, start a conversion. Now, depending on how we're playing this game, we could then pull a flag. The analog to digital is finished flag. We could sit there and read it. When it's 1, then we can read the registers. Okay? And remember, it's a reminder here. Read the low, then the high. We first talked about this in the timer chapter. There's that temporary register. So in order to prevent bad things from happening, always read the low byte first and then the high byte. Always write the high byte first and then write the low byte. And the hardware will make sure that the 16-bit operation happens atomically. Atomically just means without any interruption. And then if you want to keep reading, where are we? If you want to keep reading, just set the start conversion bit high again. That's all you got to do, over and over and over again. Unless you want to read from a different channel. So let's say you have maybe 3 potentiometers hooked up and you want to read from all 3. You read from the first one, then you got to go back and change your MUX bits. And then hit the start conversion flag. Okay, so there's a couple of things to set up. But it is a multiplexed input, so you can read from many inputs. You just have to tell it which one you want to read from. Now, there is one way in which to operate this that I have not talked about. Go back to the control status register. There is one bit that I did not talk about, and it's the date flag, the A date. It's analog to digital auto trigger enable. Date, A-D-T-A-T-E, auto trigger enable. The auto trigger enable says, hey, maybe we don't want to have to manually control the start conversion bit. Maybe we'd like it to just go as quick as possible. Let the hardware take care of it. So in order to deal with the auto trigger enable, there's actually one more field we need to talk about in another control and status register. There's the ADTS bits. trigger source. There are 8 things that can actually automatically cause the ADC to start a conversion. The easiest one to understand is free running mode. Free running mode, just as soon as one conversion is done, it'll start the next conversion. It's just always going. This is the fastest conversion possible. That is as fast as you can go. There's no processor overhead. It will just keep converting. Then there are external events. Things like, hey, when external interrupt 0 happens, when the timer does something interesting, either timer 0 or timer 1. And finally, one piece of hardware we haven't talked about, there is an analog comparator. It just compares 2 voltages. If that comparator triggers, we can also trigger the ADC. Okay, so the analog comparator is a great source of comparing analog voltages. You might have something on there like a thermistor that's just changing voltages with temperature. Only when it gets so hot will it start doing some kind of conversions. Otherwise, it'll just stay off. The only caveat of all these auto trigger modes is you got to trigger the AD start conversion bit at least once, especially in free running mode. Okay, you set up auto trigger enable and you say free run, go as fast as possible. It won't actually start right then. You have to still tell it, okay, go start the first time. And then it will go into free running mode. With the timers, they will actually trigger it every time. Now, I said one way of programming is to poll. There's obviously another way. Polling is the slow way. It ties up the processor, introduces a lot of overhead. The preferred way, what is the preferred way instead of polling? Is interrupts. And we do have an interrupt enable bit. Okay. The interrupt enable bit just means that we no longer have to poll. This is the simplest type of interrupt. We have to declare a volatile uint16. And if we're doing it in C, we don't have to worry about ADCH or ADCL. We don't have to worry about that. We only have to worry about one register called ADC, and it'll take care of it for us. In C, it will automatically grab all 16 bits at once. So if you're doing free running, all you have to do is grab the value and store it somewhere. It might be in a 16-bit variable. It might be in an array. Yeah, I don't know. Okay, depends on your application. But that's all that you have to do is grab the result out. So in the lab in phase 3 says, hey, when you press the button, start an ADC conversion. So you might have a pin change interrupt vector that just says, all right, in the ADCSRA, turn on the start conversion bit, AD start conversion. And that's your whole pin change interrupt. That's all the pin change has to do is say start the analog to digital converter. Then the analog to digital converter will trigger another interrupt. And maybe instead of my result, you put it in num to display. And then you also have a timer interrupt running. The timer interrupt, every time it triggers, it knows which of the 4 7-segment displays it's trying to show. So first it's going to do 0, then 1, then 2, then 3, and then back to 0 and 1 and 2 and 3. It's going to do that over and over again. But every time the timer interrupt fires, it should go grab num to display, do whatever shifting it needs to do to access the nth nibble, convert it, and so forth, and then display it. So these two pieces run autonomously from the rest of the code. All right? Your main loop should just have nothing happening in it. Everything should happen inside of an interrupt for this lab. It's actually not good to put large blocks of code inside of an interrupt. You want them to be as small and concise as possible. Okay. So where are we now? So that's really all there is to an ADC. It reads an analog value and it turns it into a digital value. If you so desire, let's just go over to the data sheet for a second. Okay. If you go to the data sheet, there is a whole chapter on the analog to digital converter. And right at the top, it gives you the salient points. It says, all right, it's got a 10-bit resolution. It's got a conversion time anywhere from 13 to 260 microseconds. It says that it can go up to 77 kilosamples per second, but only 15,000 samples at maximum resolution. So 76,000 at 8-bit resolution, 15,000 at 10-bit resolution. A temperature sensor, 0 to VCC input range. Okay. And we should like scan through this. The first time we talk to a new processor, we should talk about all this. And so here's all of the stuff, right? Here's our input mux. Here's our reference selection. It all goes into this ADC. There's our sample and hold comparator. Basically tells us here's all the conversion logic. All of the bits and how they relate to the conversions. There's our basic hardware block diagram. Starting a conversion, it'll give you all of the information you need. It'll even give you some sample code half the time. This is a little bit more on all of the clock timing. So if you want to know exactly how to deal with this, a couple of paragraphs on the clock timing. Even some diagrams on how long that takes. What I'm looking for is, I'm quite curious now about the temperature. Changing the reference selection, ADC input channels, analog reference, noise canceller, input circuitry, noise canceling techniques. Again, it gives you suggestions for how to keep your signal clean right in the data sheet. Even there it is. There was my my 10 microhenry inductor and 100 nanofarad capacitor. That's more on just nonlinearity. Temperature measurement, here it is. It was plus or minus 10 degrees C. So you can tell if you're in a really cold environment or a really hot environment, but that's about it. That's very funny. So it is approximately 1 millivolt per degree C, and an accuracy of plus or minus 10 degrees. It says here, like, if you wanted to, you could calibrate that and get better accuracy, but out of the box, it's plus or minus 10 degrees C. So that I do enjoy that. Blah 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 blah. Yep. So there it is. That is the ADC in a nutshell. Going back to the slides for a second, just briefly, I want to talk about the reverse of an ADC. So an ADC takes an analog value, turns it into a digital value for the processor. A DAC is a digital to analog converter. It takes a digital output and turns it into an analog output. The simplest way that you can build one of these, you can actually use something called an R2R ladder. I'm not going to take the time right now to go through how all this works, but you would hook up each of these to a port pin. So let's say you hooked it up to port D. You would have 8 outputs. Depending on which of these you tied high and low, in this configuration, you will get a proportional response for the voltage output. It's not going to be super accurate, but if you're going to be buffering this, it's going to be pretty handy. And it's relatively simple. You can do this with a bill of materials of one resistor. If you need an R2R ladder, you can use just 100 ohm resistors or just 1K ohm resistors. And what you'll do is you'll put 2 resistors in series and then 1 resistor. And then 2 resistors in series and then 1 resistor. So if you're designing this for manufacture and you just need some kind of a cheap and dirty DAC, you can do it with just a single resistor. Chances are you've got resistors somewhere on your board, so you can do this. It's not going to be able to supply tons of current. You're only, connecting this up to pins that can source 20 milliamps, and a lot of that is going to be dissipated in these resistors, but it effectively forms a voltage divider. So you would usually take this setup here and you'd put it into some kind of follow amp. That follow amp will just make sure that the voltage here is the same. The voltage here is the same as the voltage on the output, but it has a much stronger drive capability. If you choose the right op amp, it will be able to drive a lot more. So this might be, a 3-watt speaker driver. And in fact, a DAC is frequently used as part of an audio circuit. Inside your phone has digital data. It's a processor, and it does have a speaker, though. That speaker is a strictly analog device. So somewhere in here, there is a digital to analog converter. And that's all it does, is it just turns that, and then it goes into some kind of an amplifier that finally goes to a speaker, and that's how it works. Now, it might not be, and it probably isn't, an R2R ladder. It's probably some kind of a chip that is specifically designed to do audio frequencies, probably has the amplifier built in, so it's all this. It probably speaks an audio protocol like I2S, so that it can, output sound or audio data with minimal overhead for the processor, some kind of direct memory access. But at its basic, you need to convert digital to analog signals. That's perfectly doable just with a couple of resistors. All right, the last topic today is signal conditioning. And I said signal conditioning isn't going to be a big thing in this course, but any real-world device that you pick up is probably going to need some kind of signal conditioning. The basic idea of signal transitioning, we talked about it right at the beginning of class. You have the analog world. Doesn't matter what you are sampling. Where's my pen? You have the analog world. So many things to see, more to do than can ever be done. And it's going to go through some kind of a transducer. And that transducer is going to have some kind of an electrical output, either voltage, current, or resistance. You have to somehow convert that to match as closely as possible the expected range of your ADC, the positive voltage reference and the negative voltage reference. Many times that's just ground. The negative voltage reference is usually ground. Okay? Now, if it's a resistor that changes resistance, some kind of resistor that changes resistance, that's a two-ended device. You could turn that into a voltage by putting it as part of a voltage divider. And that would go into your ADC. The choice of resistance value here is going to matter, because depending on what resistor you choose, you're going to have a different swing. So you have to look at the minimum resistance, R min, and the maximum resistance, R max. and figure out what that voltage divider is going to provide, depending on your resistance. If it's a voltage, If it's a voltage, you have to look at Vmin and Vmax. If they are not really close to Vref minus and Vref plus, you probably have to apply some kind of analog gain. Everybody's been through some kind of a circuits course and should recognize this circuit. What is this circuit? It is an op-amp in a particular kind of configuration, an inverting amplifier. It amplifies the signal by some ratio, RF over RN, or however you want to label it. You might also do a non-inverting amplifier, depending on what kind of a value you need. If it's a current, Imin, Imax, current is actually pretty easy to turn into a voltage. A resistor. Now, if it's a resistor, obviously the resistance changes are going to change the voltage across it, so any small variation in temperature could affect it. You could also do a transimpedance amplifier, which is just a resistor going into an op-amp in a follow configuration. And there you go. That will also, but that again, give you a very, what am I trying to say here? A very stable output, because, why does it keep doing that? Remember, a op-amp, the basic rules of an ideal op-amp say no current flows into either of the terminals, the inverting or the non-inverting. So effectively, you have no drain across that, which means that your current doesn't have to drive anything, which is good. Okay. Now it will drop in, it'll drop a little bit, but not much. Okay. Some sensors though are nice. So there are temperature sensors, like the LM35 is sort of a jelly bean temperature sensor. You can get it anywhere. You provide it with 5 volts in ground, and it just gives you an already perfect 0 to 5 volt signal. Okay. So some things don't require any analog conditioning, but more often than not, you'll need to have some kind of analog conditioning in there to make it nice and clean. So you can spend a lot of time designing the analog conditioning circuitry. How many people actually have their own analog discovery? A few of you. Well, quite a few of you. If you ever crack that open and look at it, most of that is taken up by one giant ADC. And I've always said that device is a great deal because the ADC itself, this chip, all it does is convert analog to digital values in quantities of like 10,000. So you go to, I think it's Analog Devices makes it. You go to Analog Devices, I want 10,000 of these. What kind of a discount can you give me? They'll say to you, you can have it for $70 a piece. An analog to digital converter for $70 a piece in quantities of 10,000. If you want it in a quantity of 1, you're probably going to pay $100, $150. Okay, so they designed this thing down to a price point. It's pretty impressive, the ADC that they use. Why was I talking about this? Because around that chip, there are so many passives and little weird things going on. It's all just for the oscilloscope. That $70 chip is just for the oscilloscope. So everything around that is the analog conditioning to make sure that it can handle all of that. So it is, especially for electrical engineers that are going to be working in some kind of an embedded environment, that's where you're going to be expected to earn your bread and butter. Not only to build that circuit, but to write the code that interfaces to it. Because this circuit is going to have some kind of settling time. There's going to be time variance in there that you're going to have to be able to characterize and write the code so that you still get accurate results. And you're going to have to understand that you can only run your ADC so fast because inside of this, there's sample and hold stuff. So you need to be able to write the code and build the circuit. And if you computer engineers think you're going to get away without ever building an op-amp, you got another thing coming. We are in a very tightly woven society where electrical engineers and computer engineers share responsibility for so much. Okay? And even if you don't build it, you still have to understand what it does. Okay? Now, in none of these diagrams did I show you a single damn formula, right? Not even when we were evaluating inductors and capacitors. Because sometimes you just use what the data sheet says, and only if there is a problem do you go back to the analysis. Okay? You need to know that those formulas exist. RL circuits. You know, we've got an LC circuit in that way back here. Where were we? Much farther back than I thought. There it is. There's our LC circuit. So you might be called upon to look at the frequency response of that. Okay. At the end of this chapter, I have put in a few slides that are just code out of the book. And I'm going to skip the polling ones. I'm going to go right to the interrupt version. Okay, this version actually accesses both the ADC-L register and the ADC-H register because it's specifically splitting them up into two registers. I could have actually written this up as uint16_t temp equals ADC. That's the name of the register. It's actually capital D. Then I could have said port D equals temp shifted left by 8. Port B equals temp ANDed with OXFF. Actually, I think that is switched. This should be B, and that should be D. D gets the low byte, B gets the high byte. I think I would actually prefer it if you always just grabbed it from ADC. That prevents you from having to worry about the low versus the high. So the pertinent information here, it sets up the status and control register, sets up the mux bits and the reference selections. And then it says start. And then it sits here. It does nothing else ever again. But the ISR is going to be called repeatedly because it's going to get the data, and then it's going to trigger a start conversion again. And then it's going to go back to this while statement and do nothing over and over and over again until the next time. This is a really good idea to look at this one because it shows you how stuff is set up. Okay, and it's a pretty well working example. You're going to have to look at the data sheet to figure out what the hell 8F and C0 do. It's not super complicated. I know that in the mux register, the lower 4 bits are the mux, the choice that you want to make. And the upper bits are the reference selection. So C is a 1100. So I'm going to assume that it's chosen to use a reference of 11. So you could look that up in the data sheet. Again, in assembly, and that's just one more polling example, not that interesting. Okay, so I will see you in lab today. Discard my ink annotations. And we're going to get as far as we can in lab today. I wouldn't expect you to have any code written for phase 3, but I would expect you to at least be able to get through all of phase 1 today.